Yeah, so for obvious reasons, there's no quiz today, because if there had been a quiz today, then there wouldn't have been a quiz on Monday, and then where would we be? So got to logic those things out. So a few things that I posted on Piazza, so that's kind of the same as before, except with times. So I know that you have a thing Sunday night, which I thought was actually Friday. Nevertheless, it's good to start the project early. I know that some people have already submitted. If you haven't, there's office hours, including on Sunday. There will also be a ping pong thing on Sunday at 1:30. So anyone is welcome. So I'll get you a pass if you sign up and say that you're not from Chestnut. Yeah.
1:30 a.m.
Say it? No, it's 1:30 p.m. Thank you for the clarification. Yeah. All right. If anyone wants to challenge me to a night game of ping pong, I will consider it. So anyways, if you want to challenge me, sign up. I will donate 40 cents for every point difference for games that I lose. So if you're, yes. How often do I lose? Quite often, but I'm okay at ping pong, and I played against Chestnut people before. They're not that good at Matching. But I'm, if I'm proven wrong, I'll be proven wrong. Yes. Say it. I am terrible at pool. Sorry. So yeah. I'll practice, and next year we can play. Yeah. Okay. I'm not worried about it. Yeah, so football for the football fans, 6:30 on Monday after lecture, we'll walk over. I only am giving 25 cents for that. Not because I'm worse at football than I'm at ping pong. I'm in fact better at football than I'm at ping pong. But yeah, you have a question?
Chess. Can we do chess?
Can we do chess? I'll think about it. So say it. Yeah, and one of the past chairs of Engside's Wonka Rasinich is actually an international master at chess, and he would give. He's still around. He's an emeritus prof, and he would like play simultaneous chess against people. I'm not at that level, unfortunately. So yeah, okay. We'll think about other things. All right. Hello. Hi. All right. So more substantively, office hours over here. So I will do office hours on Monday in person after the football defeat. Whoever gets defeated. And then Tuesday and Wednesday, TBA. So the deadline for your projects is actually Wednesday. I really encourage you not to leave it until Wednesday. It's kind of an accident that it is Wednesday. But we will have, I thought about doing like a review session on Wednesday. I kind of not sure if I'm going to do that. I'm definitely going to have office hours. Okay. So that's that. There is a question here. Okay. So, all right. So today I want to do more recursion. So we kind of stopped the other day with print list and print list reverse. We'll do one more example of recursion. We'll do something more substantive with recursion and complexity that's not that difficult. We'll do a fun thing where, as it turns out, you need either loops or recursion, but not both. And I'll show you a proof that it goes at least one way. And then probably on Monday, the course will basically wrap up with how Python does sorting. So Python does a variant of the algorithm called merge sort, which is an O of n log n sorting algorithm. Kind of interesting that you could even have an n log n algorithm. We haven't seen anything like that yet, right? So we'll do merge sort and we'll do the analysis of merge sort. And this is, along with the raised to 21 example, is a situation where you can do without recursion. It's possible, but it's not super easy. So merge sort is one of those situations where using recursion is actually better. I want to note about kind of the introduction of recursion. Like, as you see, it's kind of like a mathematical thing where you figure out the recursive step. So think about it as a Blackboard presentation, the way you have in calculus, and that's why it's not going to be on the slides, it's going to be typed in. And I encourage you to type along with me in the same way that you hopefully do notes in calc, if you do. Yes?
Is there anything that you can only do recursively?
So the question is there anything that you can only do recursively? And the answer is no, there isn't. So there is, so we'll show a way to go from loops to recursion, which is easier. There is a way to also take a recursive function and implement it using loops. Kind of makes sense because, like, you know, the computer doesn't have recursion built in some sense. So somehow there is a loop that's going on in the computer. Yeah.
Is there a benefit to doing recursion?
So the question is there a benefit to doing recursion? The answer is, in terms of efficiency, no. In terms of efficiency, again, like in practice, what happens in the computer is somehow it gets converted into something that's like a loop. You'll see that in second year. So the benefit of writing things recursively is that it's easier and it's often clearer. Very often on modern system, there is not a disbenefit to doing recursion, in the sense that you don't pay an additional price in terms of runtime because you implement it recursively. So sometimes for some situations, like raised to 22, arguably, like merge sort, which you'll see you haven't seen yet, the benefit is that you write clearer code that's easier to write, easier to see through that it's correct or it's incorrect. So that's the benefit. Yes.
Like this loops.
So the question is, why learn recursion at all if loops just work? And the answer is, the sense in which loops just work is that you can, if you really think hard about it, implement something with loops. It's often really not easy, as is the case with merge sort, which, you know, I'll do the recursive version because the recursive version is like actually much easier to write. So in principle, everything, you know, eventually is just a manipulation of zeros and ones in the computer, right? So in some sense, like, why learn Python at all if everything at the end is just a manipulation of zeros and ones? And the answer is, well, yeah, like if you could write machine code directly, that's very efficient. That would be great, but often you can't. Maybe you can, but others can. Yeah. Make sense? Other questions? All right. So, okay. So we are on to doing our examples. So this is what we had last time. So this is print list and print list reverse 2, right? And the magic here, if you remember, was that print list and print list reverse 2 are basically the same, except that we flip lines 4 and 5. Make sense? So that's what we had the other day. And the effect of that was that, print list prints the list forward, print list reverse, as the name suggests, print list reverse 2. I'll try to remove my face from here. So print list reverse 2 prints 3 to 1. And that's in a way just because we flipped the order of the lines. So let's trace print list again and see what happens. So nothing too complicated, right? So we call print list, let's say with 1, 2, 3. So this is the call tree, right? So yeah, Merry early Christmas. So we call it with 1, 2, 3. The length is not 0. So we print L at 0. And we call print list with the tail of the list. So with 2, 3. Again, the length of 2, 3 is not 0. So we print L at 0. So we print 2. And we call the function with the rest of the list, which is 3. The list. The length is not 0. So we print L at 0. We print the 3. And we call print list with the rest of the list, which is just nothing. Here, the length of L is 0, so we just don't do anything. We return. Make sense? So what got printed here is 1, and then we called print list with this, and 2 got printed, and we called print list with this, and 3 got printed, and we called print list with the empty list, and nothing happened. So that's how we printed 1, 2, 3. Make sense? So now let's think about what happens with print list reverse 2. So I'm going to actually keep this call tree because it's going to look the same the way I wrote it. Right? So I call print list reverse 2. The length is not 0. So I'm going to call print list reverse 2 with 2, 3. I haven't yet printed 1. I will print 1 once the call on line 20 returns. Does that make sense? So what print list reverse 2 does is it calls this, whatever happens, happens. And then after this returns, it line 21. Does that make sense? So that means that we call print list reverse 2 with 1, 2, 3. And then this call happens. And again, nothing gets printed. What happens is the call to PLR2 with the line 3. I'm just calling this function PLR2 now. The call with the list 3 happens. Right? And again, nothing happens yet, but we call here. So now let's think about it from the top down. What happens if you call PLR2? So just to be clear, just calling it PLR2. So you call PLR2 with the empty list. What happens? Nothing, just returns, right? So that completely makes sense, right? You call PLR2 with the list that contains 3. What happens? Well, nothing, because when you call PLR2 with the empty list, nothing happens. And then 3 gets printed. So that part of the 3 completely makes sense. Or at least to me it does, right? So questions about the top of the tree so far? You call PLR2 with the empty list, nothing happens, and then you print 3. Yeah, so that's all it is. Yeah. Yeah, that's exactly. So I'm going from the bottom to the top, and then the printing happens going back from top to bottom, and I'm also explaining it this way. Yeah, like both things are true. Yes.
Start with the empty list. Where does the 3 come from?
I don't start from the empty list. What I'm saying is, if I call PLR2 with this guy, what happens? I'm going to call PLR2 with the empty list and nothing happens. And then I print the 3 with line 21. Right? So I'm just saying, like, what would happen if you did PLR2 3? And the answer is line 20 does nothing. And then line 21 prints the 3. Right?
Why does line 20 do nothing?
Well, because if this is the empty list, the question was, why does PLR2 print nothing? Because if this is the empty list, then PLR2 doesn't do anything. It just returns. Right? Okay. So who's not good with this part of the tree? All right. So now we're going to do this part of the tree. So we're thinking about it as what happens when you call PLR2 to 3. And the answer is, well, line 20, we already know prints 3 because that's just this part of the tree. And then line 21 prints the 2. So therefore, this part first prints 3 and then prints 2. Yeah.
Do you actually do it this way by like switching the colon to the other side, or would it not work? Like, do you have to start with the list being the biggest it could possibly be?
Well, so okay, so I'll take the first version of your question, which was what? So 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 what's going on here? So the second version was, can you start with the like, do you start with a bigger version of the list or the smaller? And the answer is, like, we're thinking about it as just a call PLR2 to 3, right? So we're definitely starting with this call with a bigger list, right? And then what happens is, this is a call to the smaller list. And we already said, like, with a smaller list, we know what's going on. And then we're just logicking it out, right? We're saying, well, if you make this call, what's going to happen is this call first, which outputs 3. That's straightforward. It's a list of size 1, right? And then we print the first element. So we printed 3, and then we printed 2. Okay. All right. And then this is just the same story. So this is 1, 2, 3. So what's going to happen? Well, we're going to have a call to the list 2, 3. We know that prints 3, 2. And then we're going to print 1. So that confirms that this is going to emit 1. Right? Yeah.
It's just like sequential function calls and then everything gets returned.
Right. So what you said is sequential function calls and then everything gets printed. Yeah. So what happens is this calls this, and it's still waiting around until this is done so that it can print 1. And then this calls this, and it's waiting around for whatever this does, and then it prints 2. And then this calls this, and that's very fast, just says we did nothing, and then it prints 3. So yeah, we're kind of like going up the tree, and then as we're going down the tree, things start to get printed. Yes.
I think the reason I'm confused, I don't, for some reason, understand how the slicing works.
Okay.
Can you go over that?
Oh yeah, so like the slicing, just think about it. So is it like the slicing notation, or like what did?
If it starts at 1 and then colon nothing goes to the end, right?
Right.
Shouldn't it stay as 3 or no?
No, so it starts at 1, so that means it's like everything except element number 0.
Oh, right, I forgot.
Right, yeah, does that make sense? So yeah, so let me write it down. So if L is 4, 5, 6, 7, let's say, then L1 up to the end is 6, 7, and that's because it's L except for L at 0. Yeah. All right. Make sense? So yeah, so that's kind of magical. The call tree, at least in this notation, because this notation doesn't tell you when the thing gets printed, looks exactly the same. It's just a question of, are you printing and then calling? In which case you print 1 and then you call, and then you print 2 and then you call, you print 3 and then you call, which makes it so that you print 1, 2, 3. Or is it that you call and you're waiting for the call to return in order to print 1, and then you call and you're waiting to print 2, you call and you're waiting to print 3, and then you're done, and then 3 gets printed, and now this call is done, so you print 2, and then this call is done, so you print 1. So what ended up happening is you're printing, 3, 2, 1. That's kind of the mechanistic way of thinking about it. The mathematical way of thinking about it is what we said last time, which is probably easier to wrap your head around, right? So what is this saying? In order to print the list in reverse, print the rest of the list in reverse, and then print the first element. That's just mathematically what it means to print the list in reverse. Does that make sense? So to print any kind of list, let's say this list in reverse, what do? Well, first print the rest of the list in reverse. So this is 3, 2. And then print the first element. So that's 1. And that's exactly what this recursive step is doing. So that's what we did last time, right? The mechanistic understanding, I think, is worth doing for a variety of reasons. For one, it's kind of weird that it works this way. For 2, it's good to practice with call trees. But really, if you ask, like, how do I think about this kind of thing? I think you should think about it in terms of how we talked about designing recursive functions. Like, what's the base case? Like, what's an easy case? The list is empty, nothing to reverse. What's the recursive step? Here, you need to be a little bit inventive, I think, because it's true that to print the list in reverse, like first print this in reverse, then print this. That's true, but that's maybe not obvious that it's going to work. Make sense? And we did the example last time, which I think is like a little bit more straightforward. All right. Questions about this? All right. Let's check on Discord. Okay. So what I want to do is guys, you're too loud. Guys, yeah, you have a question. Yeah. So the question is, how is it? I'll rephrase it a little bit, maybe. So how come this is smaller than? So this is like a smaller list than this, and so on. And the answer is this. So when we make the call, we are making the call with L starting from index 1 to the end, right? So if we started with 1, 2, 3, then this call is to PLR2 for just the list 2, 3, because L from 1 to the end is just 2, 3. I mean, it's automatic. It just like that's just what L1 through the end means, right? So if you say L is 5, 6, 7, then L from 1 and up to the end is just 6, 7. Right? So this is just what this notation means. Yeah. Yeah. All right. Okay. Other questions? Okay. The question here seems to have gotten results, so that's good. Okay. So one more not so difficult example. Let's say that I want to sum up a list. Right. So just okay, I don't want to compute 7 plus 8 plus 9. Like 3 plus 4 plus 5. So that would be 12, right? So by the way, so Python does happen to have a sum function that's built in. But obviously, like we want to do it recursively. Okay. So what do we need here? We need a base case. And we need a recursive step. So what's a good base case here? Anyone? Yeah. Say it.
Under 10.
Under 10. Well, no, so I'm thinking more in terms of the number of elements.
Oh, okay. 0?
Yeah, 0 is a good one. Yeah. So if the number of elements is 0, what's the sum of the list? Yes. 0. Yes. So a good number to pick. So it's a little bit weird because like you could say, well, like maybe it's undefined, whatever. But that actually happens to be good. In the same way that we said factorial of 0 is 1, we can say just define the sum of the empty list as 0. You could also say, like alternatively, the sum of a list of length 1 is what? Yeah, L at 0, yeah. Or like the only element. So either one works. I think this one kind of looks better as a finished product. But you need to think about, okay, like does the 0 actually make sense? Right? This one, like very clearly that makes sense. Okay, recursive step. So how do I express the sum of a list? Yeah. Yeah, you would. So the question was, if you're using kind of the second variant, like what would happen if you try to compute the sum of the empty list? And the answer is, well, like maybe you don't even want to define what it means to sum up an empty list. But maybe you do. And in case you do, the only option that makes sense is 0 for reasons that we'll see in a second, actually. But yeah, that's a legitimate question. Okay, recursive step. Anyone? Yeah. Well, it must be recursive, so forget variables. So I want to, I know you know. So, what we want to do is we want to express some list of L in terms of some list of some other list. Right? So let me just write it mathematically. So I want some list of L. And it's going to be equal to some list of something. And then maybe you get to do some other stuff outside. Ideas? I'll call on the guy in the back row, please. Yes. Yes, you. That's an excellent suggestion. Thank you. So, okay. So the suggestion was, well, like, what if we compute the sum of the rest of the list? Okay, sorry, I'm gonna call on you again. Do you have other ideas? All right. Well, think about it. There is another idea. But the first idea was solid. So what if we sum up the rest of the list, and then what do we need to do in order for this equation to get balanced? So you said, but maybe people didn't hear. Yeah. Add L at 0. So I'll add it here so that they're like in the same order, right? So the sum of the list is the first element plus the sum of the rest of the list. That makes sense, right? Other ideas? That is a very good point. Thank you. Do you have other ideas though? Sorry to pick on you. You have another idea? So this is not Python. This is just saying like, that's the other idea. It's like, yeah, like the last element plus the first part of the list. Yeah, that's good. Yeah.
The first part of the list plus like.
Yeah, exactly. Yeah. So you could also, so like both answers are legit. Yours is kind of similar, just like instead of L at 0 plus some list, the right part of the list do like the first part of the list plus the last element. And then your idea is, what if we are like exciting times again. I do have a charger. So I had a charger in Miami as well, just not an outlet. But anyway, so the other idea was, what if we say, mid is length of L over 2. And then we can say, well, what's some list of L? Again, this is not Python, this is just math. So we'll do the list up to mid plus the list from mid and to the end. That also makes sense. Right? So there's various ways to do it. So I will go, so this is going to turn out to be useful on Monday, or this kind of thinking at least. But I'm going to go with this right now. So the recursive step, I'll write it first because we were just talking about it. I'll say return L at 0 plus some list L from 1 and up to the end. And now I need to do the base case. Done. All right. So to the discussion from before, this handles lists that are empty and just returns 0 if they're empty. This is consistent with the other idea of just returning the first element, because if the list is of size 1, you'll return L at 0, the first and only element, plus 0. And that is kind of why it makes sense to say that the sum of the empty list is 0, is because if say, well, like if I add one more element, what's the sum going to be? It's going to be that element. Yeah. Yeah, so if you return, so the question was like, what happens if you return none? And the answer is that would be a problem, because If you then try to say like 1 plus none, that's not a thing. So you could say, I don't want to return, 0 for an empty list, in which case you would say, well, like do none for length 0 and then do the first element for length 1. Yeah. All right. So that's some list. Questions about this? Yeah. Sure. Okay, let me try. So have plans here. So this is basically the alternative to mid to just tell it 0. So we'll call it sum list 2, I guess. And what we're gonna do here is, like, I'm literally gonna copy and paste this, but there's gonna be like a tiny complication. So that's a sum list, of course. So sum list 2. Sum list 2 like this. Okay, so this is just like translating the math into Python. Like, what does it mean to sum up the list? Is like sum up the first half, sum up the second half, add those up. The complication is if I do it this way, and if I have a list that's of size 1, then the way it's going to be split up is like one of the halves is going to be, again, of size 1, and one of the halves is going to be empty. So we're going to have infinite recursion because we're always going to have a half that's of size 1. So for that reason, and I don't want to, like, if you trace it, you'll see, I also need to say, if length of L is equal to 1, return L at 0. Otherwise, it's just this formula, which is, like take the list up to mid and take the list starting from mid and up to the end and add those up. Yes.
Is that the full function? Like,
Yeah.
Are we never like extract the elements of the sum up? Like,
we do over here.
Oh.
Yeah. So that's actually, that's like a good way, another good way of thinking about it. So what McKelly said is if you, yeah, I saw your name at the, oh, you introduced yourself at the event thing. Okay, so what Callie said, I hope, is that like if you do it like this, like where exactly is it that you're getting the values of the elements? And the answer is over here. So when the list gets to be of size 1, then you're extracting the values of the elements. Right? So that's another kind of argument. Like what I did is give kind of a mechanistic argument for what you're going to do when the size of the list is 1, because you're going to split up the list into size 1 and size 0. So for that reason, I said, well, like you got to also check if the length of L is 1. What do you do? Your way of thinking about it, I think I like better, which is, well, like at some point you got to actually extract the values of the elements. So like it's got to be that you have to have this. All right, that's very good. All right. Other questions? Cool. So I have the chance to tell you about one more thing. It's great. So what we've done in the lab, so you've all hopefully done it, is x to the power of n, right? And how you do it, well, it's the same as the factorial, really. So we'll say, if n is equal to 0, it'll return x to the 0 is 1. So by the same reasoning, by the way, you might say, well, what's x to the 0? Well, the only thing you can say is 1 because otherwise everything breaks. And else you hopefully said return x times power x and minus 1. Make sense? So everyone did it, right? So like that makes sense. Yeah, no objections? Okay. So what would the call tree for that look like? Like nothing surprising, right? So it's like you call it with n and then n minus 1 and then n minus 2 and so on up until you get to 0. And then you return. So that's the call tree, right? So I now might say, okay, what's the runtime complexity? And the answer is, well, what is going on here? We make n plus 1 calls. Each call takes the same amount of time. So let's say that amount is T1. So total runtime is what? N plus 1 times T1. So proportional to n. Okay. There is a subtlety here, which is that the times, well, if you assume that it takes the same amount of time, then it takes the same amount of time under your assumption. Of course, if x is actually an integer, then multiplying two huge integers is going to take more time than multiplying two small integers. Floats, however, are fixed size, so they can only get so large. So multiplication for floats actually does take the same amount of time. For that reason, if you look at past exams from recent years, I'm always careful to say nothing is an integer, it's all floats. And that's so that the arithmetic operations don't start getting out of hand. Right? So for floats, this assumption is correct. Okay. So that's O of n. Why is it O of n? Well, because you make approximately n calls, and each call takes the same amount of time. So it's like counting iterations, except you're counting the amount of calls. Yeah.
Was it n plus 1 calls?
It was, but it's proportional to n for a large n because T1 is much smaller than n times T1.
Why is n plus 1?
Oh, why is it n plus 1? Well, because you go from 0 to n. So it's like if you go from 1 to n, that's n. If you go from 0 to n, that's n plus 1. Make sense? So here, like I'm counting the calls over there, and the calls go from like n down to 0. So like think about it like, like if it's like 1, 2, 3, that's 3 calls. If it's 0, 1, 2, 3, that's 4. Right? It's not about up or down. It's about, do you include 0 or not, right? So if you don't include 0, like 1 to n, like n equals 3, that's 1, 2, 3, that's n. 0 to n, that's n plus 1. Make sense? Okay. So what I want to do is ask, okay, can we do better? And this actually has to do with the thing I was bothering you about before. Okay, so can we do better than O of n if we're computing x to the power of n? As it turns out, yes. So here's the idea. So if I take x and then I square it, and then I square the thing again, and then I square the thing again, and so on, I can get to a very large number very fast. Each squaring is what? Is like left-hand side times left-hand side again, right? So, oh, okay, well, I just have 4 minutes. It's okay. So this is going to be x times x. And this is going to be x squared times x squared. And this is going to be, luckily, I have copy paste. This, right? So that's just what squaring means. Make sense? So that means that in order to get to x to the n, I don't have to just like wait around like times x times x times x times x, which is what I was doing before. I can get to n very fast. Right? So can we use this in order to implement power, and can we do it recursively? The answer is yes. So the base case is going to be the same, except again, for the same reasons, I'm going to do like x equals 0 and n equals 0, n equals 1. Right? So x to the power of 1 is x. And now instead of kind of decomposing x to the n into x to the n minus 1 and x, I'm going to decompose it into essentially x to the n over 2 and x to the n over 2. Right? So I'm going to say this is approximately this much. And I'm going to say this is like this. So now I have x to the power of n over 2. Right? And now what I need to do is square it back and possibly add a little bit if this was actually rounded down. Right? So that's going to be half power times half power. So it's important to define the half power because if I make 2 calls to power fast, that's not efficient. So I save the answer to what x to the power of n over 2 is. So this is going to be in math what? X to the power of n over 2 times 2. So this is either x to the n or it's x to the n minus 1. So, okay. So now say, well, if n mod 2 is equal to 0, I'll return almost full power. Else, I'll multiply it by x so that it's x to the n fully.